We just made it through Chapter 3, which was the introduction of limits and learning how to work the limits. And now we're going to continue working those limits to apply them to one of the biggest problems in calculus, the tangent line problem. So here we go. Just a quick thing is displacement, and how we're using it here is displacement is the change in position over a certain given time, and velocity then is the rate of change of that displacement. So here we have Brad, or should I say Beebs, and he's trying to get to a concert, and so he's just kind of running, dancing along to get there. And what we have is this chart that represents the time in seconds and then the distance that he's covered. So x is our independent. Down here on our graphs, x would be the independent, it's how much time has elapsed, and then y is the dependent, it's how far he got given that time. So if you do look at what he's doing here, just like when we're talking about rates of changes of your car, so we're on the highway, how they give us those are miles per hour. So we're going to be talking speed or velocity here, and what that is that average speed that you should be going. So when Brad, after 1 second, let's look here, I'm just going to look at that first vector that we have, and he would have gone a distance of 1 foot. So down here I have that also represented. If I were to ask you what is his speed, what is his speed after 1 second? Well, know that that would just be the displacement, which is 1, divided by time, which is 1. So 1 foot per second. Okay. Here, if I were to ask you, and I drew him wrong, Beebs, you should be here. Sorry. So he should be right there. And if I asked you after 2 seconds what is his speed, well, understand this. He did end up going a little bit faster in that 2 second. He was speeding up, but still, if I'm going to ask you what is his average rate, this distance he has covered has been 4, and then this distance, or that time, has been 2. So overall, once again, he should be here. So overall, he has gone 4 feet in 2 seconds. So his average speed would be 2 feet per second. Okay, and then finally here, this one's going to be, let's go by points. We have the point 3, 9, and then this is our 0, 0. Using that good old y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, which is just the rate of change, which is the slope of this line, which is also the average speed that Beebs has been going. It'd be 9 over 3, which is going to be 3 feet per second. Okay, so keep in mind that these arrows, I don't know if I drew that in the right place, I probably didn't. And then keep in mind these arrows are kind of, the vectors have been increasing in length, in magnitude. But overall, if I were to just ask you over this whole span of time when he's gone 16 feet in 4 seconds, well, we tend to average those out, so he'd be going 4 feet per second. So, yay, he got to his concert in time. Very nice, guys, by the way, very nice. Alright, so secant line. What we're talking here is the average rate of change between 2 points. Here's 2 vocab words, but I'm going to go into depth about these here in a little bit. A secant line is a line that passes through 2 points on a curve. A tangent line, on the other hand, is going to be passing through 1 point on a curve. So there's an image. All of this leads to the tangent line problem. Let's say that I were to ask what was Brad's rate of change, or his speed, right at time equals 1. So x equals 1. So if we could stop at that very instant moment and figure out what was his speed, that's what I'm looking for. And unlike with the secant problems where you have 2 values where you could find the difference of the y's and the difference of the x's, our points are right on top of each other. I'm finding what's the difference at this point minus the difference at this point. So our y values would be 1 minus 1 over our x values, which would be 1 minus 1 as well in this particular instance, and we would get 0 over 0. That's confusing as well as just garbage, so we can't really do anything with that. But you can clearly see there is a slope of a line that's going through this point. So how do we find it? Well, that's where a whole new slope formula comes in. This is our new and improved slope formula. Instead of y sub 2 minus y sub 1, it's going to be this. However, what I want you to know is these are actually the same thing as y sub 2 minus y sub 1. Up on the top, it is the change in the y's, and then on the bottom is the change in the x's. Exactly what we were doing before. Delta x, this symbol just represents change in x. We're going to go back to the secant line problem. Let's say that we're looking at this point right here. So at x equals, we're not even going to say that this is 1 comma 1. Let's say we don't know it. So I'm just going to go ahead and say this was our starting point, x comma f of x, right? And this point right here on our graph would be, let's look at the difference between here and here and say that there's been a change in x that has occurred. So this point, whoever cares what this point was right here, we know that it was from that starting point an x plus a change in x has occurred to go from here to there along our curve. So the x value that we started out with plus a change in x, comma, then the value of this y would just be us plugging in that x plus delta x, whatever this particular value is, into that function. Okay, so now going back to our original y sub 2 minus y sub 1, this is our y sub 2. So I'm going to take f of x plus delta x minus our y sub 1, which was just f of x. Okay, all over, and then we would have our x value, our second x value, which is x plus delta x, minus, and then our x. When we cancel these out, those are gone, and what we get was that difference quotient that we just went over. So you can see how y sub 2 minus y sub 1 is completely the same. In this case, or y sub 2 minus y sub 1 all over x sub 2 minus x sub 1 is the complete same thing as our quotient function. So now, if I were to say and define this, this is going to be delta x equals 1 here because we can see the difference in our x's are just a distance of 1. All right, let's look at this and say here is our original starting point, x comma f of x. And then here we're going to say is our second point. So the change in delta, or the change in x here is just going to be delta x is approximately 0.5. But once again, what we're dealing with here is that this is going to be an x plus the delta x, the change in delta x, and then comma f of x plus delta x. Alright, so what's happening is, I'm going to start with this line. The delta x was 1 here. Delta x is about 0.5 here. Delta x is 0 here. If you did go ahead and plug in then that we have an f of x plus delta x minus f of x all over delta x, being that this would be 0, you'd still have just f of x minus f of x over 0, and that would still be problematic for us, except for that's where wonderful calculus comes in and saves the day. So pay attention here. This is the new definition of a derivative, or this is our new definition, which is a derivative, and all that is the slope of the tangent line. Here's one notation of it. We're going to come across different notations, but this is what we're calculating. It's the limit as that delta x approaches 0 of our difference quotient, which is just our slope. So this will get us that. It will give us some sort of function that allows you to calculate that instantaneous slope line at any given point on that curve. It will give us that instantaneous rate of change. So this is our new vocabulary. I just wanted to bring this up, but secant would be the average velocity, and if you took that secant and let that change in x tend towards 0, then what we're doing is we're letting that tend towards a tangent line, and our tangent line is the instantaneous velocity. Derivative is just the slope of that tangent line. Here's different notations that we have. I particularly like these two just because this is, you can take it literally. What this is the change in y over the change in x. So we're saying that that is equal to what? We're going to be coming up with these various formulas or various functions that will give us that ability to figure out what that rate of change is. What this brings us to is the definition of a derivative. And what it is, it's a slope. It's that slope of the tangent line. It's a function that will give us or allow us to calculate the instantaneous slope at any given point along a curve. Alright, let's do one. So you're going to be a little bit weirded out by the answer, but we'll have a discussion on that. So we're going to be using, it asks us to find the derivative by the limit process. So in other words, we are going to be using this. Okay. And one thing that I would like to throw out there is a lot of textbooks have gotten into the habit of using h for your delta x to represent that change in x. So you can look at it like this if you want. It does help sometimes with the whole process, but I am going to use delta x, but go ahead and use an h as a substitute for delta x instead, because delta x is just one quantity. It's the change in x. It's some sort of change in x. It's just one specified quantity, and it looks confusing because people look at those two symbols and think it's two. But here we go. We're going to be doing the limit as delta x approaches 0. And this first piece right here, f of x plus delta x, if I were to ask you just separately on its own, what is f plus delta x? Well, you would be taking this and plugging it in for your input for your f function. And so it would just be 1 minus x plus delta x squared, right? So that's exactly what I'm going to put here. And then minus, if I ask you what is minus f of x, well, what is f of x? Hey, it's right here. So I'm going to plug that in. 1 minus x squared. All over delta x. So this is going to be equal to the limit as delta x approaches 0. And I'm going to go ahead and simplify this piece right here because it deserves to be FOILed out, because it's not just x squared plus delta x squared, because you can't just distribute that too. It's this. We're trying to look at and figure out what is this equal to. And that deserves to be FOILed. So we have 1 minus, this is x times x, which is going to be x squared, plus we have the outsides, which would be x times delta x, and then plus the insides, which would also be x times delta x. So I'm just going to go ahead and write 2x times delta x here. Okay, and these do need to be in parentheses, by the way. And then plus lasts, so we're going to take those, plus delta x squared, that little quantity squared. Alright, minus 1 minus x squared. So make sure this is also in parentheses because they said subtract all of f of x, not just a part of it. So we need to subtract all of f of x, and distribution will play a role here in the end. Okay, so now we're going to continue on. The limit as delta x approaches 0. And yes, I put this in all the time because I need to remind myself that that is what I'm actually trying to calculate here, the limit. And I couldn't, first of all, you could try to directly substitute this in at the very beginning, but we got that 0 on the bottom, and that's hopefully what I hope through all my algebra manipulations, to just be able to cancel that factor out. So we need to simplify all this. We have 1 minus x squared minus 2x delta x minus delta x squared minus 1 and plus x squared all over delta x. Alright, let's simplify more. And I'm going to tell you straight up right now that you should have only terms left with delta x in it. This will happen every time if you did it right. So minus 1 and plus 1, they cancel each other out. Right? Negative x squared and positive x squared will also cancel each other out. What I have left is negative 2x delta x minus delta x squared on the top all over delta x. And here you have a delta x in this term, a delta x in that term. I'm going to divide out, use that handy dandy manipulation process of dividing out or factoring out. I'll take that delta x out. What do I have left if I take delta x out of that term? Well, negative 2x minus, what do I have left if I took out the delta x from that term? A delta x all over delta x. These are gone, and that was my problem factor. So now, finally, beautifully, we have delta x as it approaches 0 of negative 2x minus delta x. And take that delta x, sub this right on in there. So what this whole limit is, through direct substitution, is negative 2x. This right here is my derivative. It is, I'm going to go back, it is the function. This is what we have f prime of x is equal to negative 2x. Or we could have called it dy. The change in x, or the change in y over the change in x is negative 2x. This allows you to calculate the instantaneous slope at any given point along the curve. Notice up here we were finding that instantaneous rate at that exact point. We're not doing it at an exact point here. So notice how the rate of change will change as you pick different tangent lines on this slope. So over here it's going to actually be negative slope. Over here it's positive. So this, by having that variable x in it, you could find, let's graph this. Let's squeeze this in here. This could also be written as negative x squared plus 1. So it is our quadratic formula that's lifted up 1 and flipped downwards. Okay, so if I were to say, let's find the instantaneous rate of change at 1, we'll plug in 1 here. What we're going to get is f prime of negative 1. That would be negative 2 times negative 1. We're going to get 2. What? Oh, sorry. Let's plug in, this is negative 1. Alright, let's plug in negative 1 right there at that slope, or right there at that particular instantaneous point. That rate of change, how fast Brad would be moving to get to the concert, would be 2 feet per second. Alright, f prime of 1, so at this point right here, now this is going to be negative 2 times 1. That rate of change, or that slope, is going to be negative 2, so it's going down. So it all, this derivative, what we get in the end, is going to be a possibly some sort of, what we get in the end is some sort of function, some sort of equation that allows us to calculate at every single point along this curve what is the rate of change. So at a specified point versus overall derivative, we can do one exactly, we'll do one exactly from your book. So let's do 5, f of x equals 3 minus 2x, and they ask us to find the slope of the tangent line to the graph of the function at the specified point. So find the tangent line, the slope of the tangent line, so we want to find the derivative at this particular point. So here's our function. Let's go ahead and use our derivative equation. So the limit as delta x approaches 0. Alright, and we're going to be doing f, I'll just write it out because we're new at this. We might as well get practice writing it out. Here's my difference quotient, our new way of calculating slope. And this is going to be the limit as delta x approaches 0 of, here I'm going to go ahead and plug in 3 minus 2 times x plus delta x, because I just took my function and I plugged in for x this input that they're asking for an x plus a change in x, okay, minus the original function, which is 3 minus 2x. Don't forget to put that in parentheses. Sorry, everything's so sloppy. Okay, and then all over delta x situations. We have limit as delta x approaches 0 of, let's see, what can I cross out? These go. Okay, these go. We have negative 2 delta x over delta x. Alright, these cancel each other out. Alright, what's the limit as delta x approaches 0 of negative 2? This is one of our basic limits. It's a constant, so this is just going to be negative 2. Alright, what is this saying? Negative 2. What did I just get over finishing, or finish telling you? That it could change. It varies. If you have a curve, the derivative will vary as you look at different tangent lines. Well, now consider this one. What's going on with this function? Our original function that if I were to graph, so here's my f prime of x, or in other words, if you want to look at it as dy dx. So here we had f of x is equal to 3 minus 2x. So again, this is going to be up 3. You could write it as 2x plus 3 instead of 3 minus 2x. And we have this negative slope of 2 down 2 over 1. So that is what my function, my original function, looks like. So if I were to ask you, well, what is the rate of change of this versus what is the rate of change of a graph that looks like that? The rate of change here is changing as you pick different points along that. Is the rate of change here changing? It turns out that the derivative is actually going to be right on that line, so it doesn't actually cross through exactly one point of a curve. It crosses, it's actually that line. The rate of change here is just the slope of that function, which is negative 2. So if they were to ask me then at this particular point, well, what is f prime of negative 1? Plug in negative 1 into this function. Well, it's just negative 2. It's always just going to be negative 2.